And the name of the topic is vector and components. So if the object is in the state of the equilibrium, in this state, acceleration in the object must be zero. And this is only possible when the object is at rest or moving with uniform velocity. In the state of the equilibrium, acceleration in the object must be zero, and acceleration zero when the object is at rest or moving with uniform velocity, not speed. Velocity is a vector. So we will write uniform velocity. Then vector sum of all forces acting on the object must be zero. The vector sum of, if the vectors are added by head-to-tail rule, then their vector sum must be zero. For example, this is the pendulum. It is displaced from this position. This is the actual position of the pendulum, but it is displaced through angle theta. One force which is acting down is the weight of this pendulum bob, and this is the tension, the string, and you are holding the bob with force F. So three forces are acting. Number one, number two, number three. So it is at rest, in the state of the equilibrium. Then the vector sum of tension, force, and W must be zero. And we have to show this by drawing. Look, suppose we draw first the vector weight downward. Number two, your force. This is F. And the third, tension in the string. So it is in this direction. So look, the resultant is zero. It's a closed triangle. Hence, resultant force is zero. So when these three forces are added by head-to-tail rule, the resultant is zero because we started from this point, and then F is added, T is added, and the end also at the same point. The sum of these three forces is zero. So the object is at rest or in the equilibrium. Number two, if the object is at rest or moving uniform velocity, mean the resultant force is zero, then number one, sum of all x components must be zero. Three forces. So the x component of the F plus Tx plus Wx must be zero. The x component of all three forces must be zero. And number two, then sum of all y component of all forces must be zero. When their y components like Ty, Wy, Fy are added, answer must be zero. Okay, now the application of components. We have done one application, the components of the forces at a slope we have done. Now this is application example number 2 of components of the forces. Suppose one of the object is hanging with weight W with the help of the two strings, number 1 string and number 2 string. Both strings suppose inclined at the same angle with the horizontal line. This angle is theta, this angle is theta. Now the tension in the string is T, and the tension in this string is also T because both angles are equal. So do remember, if both strings are making same angle with the horizontal line, then their tension will be same. Now this object is hanging, it is at rest, no acceleration in it, so it is in the state of equilibrium. Three forces are acting, and the vector sum of three forces is 0. Look, this is weight, number 1 tension in this direction, and the number 2 tension in this direction. So look, it's a closed triangle. So the resultant of the all forces is 0. So when we will add three forces, weight, right side tension, left side tension, by head to tail rule, there will be no resultant 0. It means the object is in equilibrium and acceleration 0. Now, according to this rule number 1, that the sum of the x component must be 0. So we will resolve them. We will break them into their components. Look, this is the tension right side. So the line adjacent to the angle, this line, this one, is called is x component. And the line perpendicular to this one, is its y component. Similarly, this left side tension, so the line adjacent to the angle, this line is its x component, but it is directed towards the left. So this component is the negative, and its y component is also exactly upward, so ty. So tx Ty for the right side tension minus Tx, and the Ty for this left side tension, and the weight is acting exactly downward, so its x component 0 and its y component downward is the vector, is the weight itself. We have done this. Now first we add all x component, so this right side tension, it is Tx plus left side tension, it is Tx minus, and the weight component is 0. And according to the principle, the sum of all Tx must be 0. Look, this Tx is T cos theta minus Tx is also T cos theta plus 0 is equal to 0. Both tensions are same, both angles are same, so it's cancelled, hence proved it's 0. So when object is in the state of the equilibrium, resultant force 0, then the sum of all x components must be 0. This is very important. Now come to the y component. From this, we will derive the formula to find the tension in the string. Look, Ty This is Ty upward positive, Ty upward positive, but this y component downward is a negative. According to the rule, the sum of Ty upward, second Ty upward, and the third y component wy, which is minus, sum must be zero according to the principle. Now we can write Ty, T sine theta, Ty, T sine theta minus Wy, and look, the Wy exactly equal to the W because it's acting vertically downward. So T same, angle same, we can write 2T sine theta is equal to W. Hence, tension in each string can be determined by W divided by 2T sine theta. So this is a very, very important formula to calculate the tension in the string when both angles are equal. For example, this weight is 25 Newton. This theta angle is 60 degree. This angle is 60 degree. And the question is, by calculation, find the tension in each string. So we will use this formula. T is equal to weight 25. Sorry, this is 2 sine theta, okay? Because tension is here, so W divided by 2 sine theta. So 25 divided by 2 times sine of 60 degree, we will calculate this, and this will be the answer for the tension for each. So this is the formula to calculate the tension. Now, if the question is, determine the tension in each by drawing, not by calculation. So first of all, look, this weight is 25 Newton. We will draw the line for the weight. Suppose the scale is 1 centimeter represents 5 Newton. Then for 25 Newton, we have to draw 5 centimeter line downward. So with the help of the meter rule, we will draw this line 5 centimeter representing 25 Newton. And then this is the vertical line. And here, this angle 60 degree is with the horizontal line. But we have to calculate, we have to measure the angle with the vertical line. So if the horizontal angle is 60, then the angle with the vertical line will be 30. So this tension, number one, is making 30-degree angle with the vertical line. So at the angle of 30, with the help of the protector, and we will draw here a tension. So in the drawing, we will use the vertical angles. Similarly, on the left side, look, this 60 degree is with the horizontal line, and we will measure this angle, which is 30. So we will draw here 30-degree angle with the help of the protractor, and then we will draw a straight vertical line. So this line will represent right side tension, and this will represent left side tension. By measuring the length with the help of the ruler and then multiplying it by 5, we will calculate the tension, and this answer will be exactly equal to this. So this is the formula to calculate the tension, and this is the method to determine by drawing. So do remember, instead of the 60 degree, we will use 30 because this is the vertical line. So we have to draw here the vertical angles of both. Mean the angle of each tension with vertical line. So this segment, this portion of the line representing right side tension, and this will represent this. So we will measure it and we will convert it into the Newton because this is centimeter, 1 centimeter representing 5. So suppose this is 3 centimeter, we will multiply it by 5. So answer will be like 15. But we have to calculate it, we have to measure it according to scale. Okay. Same example. Suppose this is the rope and it is pulled by two persons in the opposite direction. Both are suppose exerting the same force, same tension. No one can make it 100% horizontal. If it is horizontal, then the horizontal angle theta becomes 0. So the weight requires the vertical component. So vertical component is measured from the sine theta. So sine 0 will be 0, so it's not possible. So when a rope is pulled at the both ends in the opposite direction, it has some angle with the horizontal line like this. This is theta, maybe 0.5 degree, maybe 1 degree. So we cannot make the rope 100% horizontal because when it is horizontal, then the y component becomes 0. So the weight is still requiring the vertical component. So this is Tx, this is minus Tx balance, weight is here. So this weight requires the vertical component Ty and Ty. So we cannot make the rope straight horizontal because weight is acting downward. So upward forces or force must be required to balance it. So this rope at the center is making some angle with the horizontal for its vertical component. Now the next application or the example, suppose this is the object of some weight W or W is equal to mg. It is hanging with the help of the two strings, but two strings are making different angles with the horizontal line. Look, this angle is different from this angle theta 2. Now, this tension will be different, this tension will be different because angle different. Now, tensions are resolved into components. So this is T1x, and this side it is minus T2x, and the x component of the W is 0 because it's 100% vertical. Now T1x is this. Similarly, T1y in upward direction and T2y also in the upward direction. It is at rest, system is the equilibrium. So sum of the all three forces T1, T2, W will be 0. I mean the resultant will be 0. And now the x component, look, T1x plus minus T2x and plus 0 is equal to 0. Mean the sum of the x component must be 0. So it can be written as T1 cos theta 1 minus T2 cos theta 2 is 0. So this is the first equation. Similarly, we can add y components. So T1y plus T2y and plus the vertical component of the weight is minus W because downward. So we can write minus W 0. So T1 sine theta 1, T2 sine theta 2 is equal to W. This is the second equation. By solving these two equations simultaneously, we can calculate T1 and T2. But by drawing, first of all, we will draw line for the weight. Then look at the angle of the T1. Suppose this is 60 degree and this angle will be then 30 degree. So we will draw the vertical angle here 30 degree. Say this is 30 degree and this is representing T1. Now come to the second. This angle is suppose 70 degree. So this angle will be 20 degree. So here with the vertical line, we will draw this angle 20 degree. So this portion is T2. So we can calculate either by this numerical method by solving these two equations simultaneously or by drawing the vectors. So this is the easy way to determine the tension T1 and T2 instead of this calculation. Now it's up to you.